All right, today we're going to talk about relative abundance. So we're going to be talking about a couple of things that we've been learning in some of the other videos. On your periodic table, you've been learning how to take a different element and you can come up with the protons, neutrons, and electrons very easily. You take the decimal number, make a whole number, and then you subtract and you've got your answers. Okay, so for example, we're going to deal with oxygen here for a minute. Oxygen is 8 and 15.999 rounds to 16. And so what you knew very quickly was that oxygen was 8 protons. What's the only other element that has 8 protons? Nothing. If you change the protons, you change what element it is. So oxygen is the only thing in the world that has 8 protons. If it has 8 protons, it had 8 electrons. And then you round that to 16. 16 minus 8 was 8 neutrons. That was really easy to do. But what we're going to learn today is why is this a decimal? Okay, it's called relative abundance. Now, scientists have been studying elements for a very, very long time. And they know that, for example, in the case of oxygen, there are 3 versions of oxygen. There are oxygen 16, oxygen 17, and oxygen 18. Now, the most common oxygen in the world is oxygen 16. Why? It's the closest to that decimal. So if you actually wrote it like this, that would be fine. Okay? What do you call things that have a dash and a number like that? Dash and a number. Yeah, they're isotopes. In this case, they're heavier versions of the same element. So they have different numbers of neutrons. Now, as scientists have studied them, I don't want to count protons, neutrons, and electrons. What I want to know is where does that number come from? And here's what happens. If you take a pure sample of oxygen, scientists have studied it in depth and found that pure oxygen, I'm going to go ahead and put the 16 back on here, that 99.757% of all oxygens in the world are that version. They know that 0.038% of oxygens in the world are oxygen 17, and 0.205% of oxygens in the world are oxygen 18. Okay? Now, notice all 3%, they probably with 99 they add up to 100%. So if you have a pure sample and you had to guess how much do most oxygens weigh, they weigh 16. What's the rarest one? Well, by the percent, I can tell that there's not a whole lot of oxygen 17 in the world. Okay? So what we're going to do is we're going to use these numbers to help us. Now let's pretend on another example that I had 3 guys and I wanted to know how much their average weight is. So I asked them their weight. One guy says I weigh 150 pounds. Another guy weighs 162 pounds. And the other guy weighs 185 pounds. If I want to know the average, what do? Add their weights, get a grand total, divide by 3. Do any of these guys weigh the average? Probably not. It's going to be somewhere in between all of their weights. And that's exactly what's happening right here. We're going to take this data that we have, and we're going to come up with the average oxygen weighs on the periodic table. So we're going to be using percentages. Well, very simply, here's what we do. If this guy weighs 16, and I know that the percentage is this, well, anytime you use a percentage for mathematics, you drop the percent and you back the decimal up 2 spots. So what we're going to do is we're going to take 16 times 0.99757. And we're going to take the next one, 17, and we're going to multiply it by, back it up 2 spots, 3 zeros, 0.00038. And then on this one, we're going to take 18 times, back it up 2 spots. That's 2 zeros, 0.00205. And what that's going to do is it's going to end up giving us the average when we get to the end. And I'm going to show you how to do it. I'm literally going to do this on my calculator with you. So grab your calculator. Oh man, if you don't have your calculator, pause the video. Get your calculator, come back. You need to do this with me. Now here's what we're going to do. We're going to take 16 times 0.99757. We're going to write, that's what I get right there. I'm going to write all of it down. Now, it's really important that I say this right now. When you do relative abundance, you do not do sig figs. So, and you'll see why here in a second. 15.96112. That's the number I need. Do the next math. Clear my calculator. 17 times 0.00038 equals. There's the answer I get there. We've got 0.00646. And the last line, 18 times 0.00205 equals. There's the number I got. 0.0369. Now, All three of these percentages added up to what? 100%. So that means all of these weights equal 100% of how much its weight is. So we're going to add these three numbers. So I'm going to take that number I just had, add the other one, 0.0646 plus 15.96112 equals 16.00448. That's the average. Look how close that number is to this. I can tell I did it right. You may be thinking, well, why does the periodic table have that number and we got that number? Well, I'm going to show you here in a second, but see how close it is? That's the answer. You don't do sig figs here. You're going to take the decimal, whatever pops up on your calculator, you write it all down and you add them together. Now, let's do a couple others together, and as I do the others, it will make sense why on that first one. Now, I have some others. I've gotten ahead of you a little bit, and so if you have to pause and write them down first, do that, and then we'll do them together. There are 4 versions of lead in the world. There's lead 204, there's lead 206, lead 207, and 208. First thing I want you to notice, is there a lead 205? No, it doesn't happen on Earth. And so we don't have that, okay? And so we want to make sure we catch that. There is not, just because I want it to be there doesn't mean it's there, okay? So I'm just going to go ahead and do this real quick. I'm going to back the decimal up on each of these real quick. 1, 2, 1, 2, 1, 2. And then I'm ready to multiply. All I'm going to do is take the weight times that percentage and write it down. Okay, so I'm going to take 204 times 0.014 and write everything down. 2.856. Take the next one, 206 times 0.241 equals 49.646. You should be doing this math with me, checking your work. 207 times 0.221, 45.747. Last number, 208 times 0.524 equals 108.992. So what do I do with those numbers? You just add them together. .646 plus 2.856. Write it all down, 207.241. Check my math, see if that's what you got. 207.241. I want to show you something that's really interesting. I'm going to try to zoom in real quick right here at lead. Lead is right there. See if I can make this thing zoom a little for me. See, it says 207.2. Look at the answer we got. Let me refocus. We got 207.2. We're right at that answer. We did awesome. Okay? Let's try the next one. Okay? Pause the video this time. You work it, and then when you hit play, I'll come back and check your answer. All right, I'm going to go back 2 spots, 2 spots, and 2 spots. Wow. So uranium, there's 234, 235, and 238. Notice there's no 236, 237. Those isotopes aren't found in nature, or scientists haven't found it yet. Okay, so we're going to do our math here. 234 times point. There's 4 zeros. 1, 2, 3, 4, 5, 5, and write it all down. It's 0.01287. Next one's 235 times 0.007200 equals, and then I'm going to write it all down, 0.00252. Next number, 238 times 0.992745 equals 236.27331. Then I add them together. Now I think I pushed the button wrong, so I'm going to try it again real quick. 234 times 0.123455 equals, got it? Got that one right. I'm going to show you why I think I did. times 0.007200 equals, yep, I missed this number right there, 1.692. See, even I make mistakes. I'm going to check my last one also. 238 times 0.992745 equals, got that one right. So add the numbers together now. 1.692 plus 0.01287. Then I don't get that. I got 237.97818. How did I know that was right? Well, look at my percentage. I'm at 99% is this. So my final answer should be really close to this. There's a small percentage. These two are lighter. So this and this percentage are going to bring it slightly under 238. And I had right under 238. It's 237.9. When I dropped all the way to 236, I knew it wasn't right. Okay? So when I look at one like this, 52% is 208 and 22%, okay? So basically, it's going to be pretty close to 208 because over half of it is this weight, and you can tell I'm pretty close. Now, with the third one, it just looks really different. Pause the video and look at it real quick. Okay, here's what's happening. You can do these in two ways, okay? Copper 63, copper 65. Notice there's not a copper 64, there's not a copper 62. These are the two there are, okay? But I have this weird number here and then the percents. So here's what really happens. When scientists take a sample of pure 63, the actual weight is 62.9. So if somebody says, I weigh 150 pounds, and you step on the scale and it says 150 pounds, if you had a scale that was super, super accurate, do you think they weighed 150.0000000? No. They're probably slightly off. They might weigh 149.99964. But that's like 150. Well, this is the actual weight to 1, 2, 3, 4, 5, 6 decimals. So here's the deal. If you ever see a number as a whole number like these, man, you can do your math and you can work it. But if they give you the real weight, you just want to ignore these two. So we're going to use this as the weight, and we're going to do the same math. Back it up 2 spots, back it up 2 spots, and we're just going to use this number times that. Okay? So let's see what we get. So you got to be careful with your typing because you saw I already missed one. 62.929601 times 0.6917. Write it all down. 43.52840501. Next one, 64.927794 times 0.3083 equals, write it all down, 20.017238889. You should be doing this math with me to make sure I get it right. Make sure you know what you're doing. Add them together. So I'm going to take that number plus that 43.52840501. My answer, 63.545639. So basically it's 63.5. Let's see how close we got with copper. On the periodic table, copper's right there. .546. Look at that, 63.5, 4, and 6 if we stopped right there. So back to the first question we ever did on here. Why did I miss the weight from the actual weight? Well, I didn't have the full weight number like I did on this one. Let me clear that up a little bit. I didn't have the full weight numbers. Notice the better the numbers, way better answers. So I started by teaching the skill using whole numbers, 16, 17, 18. I bet their weights aren't exactly 16, like the problem we just did. The better the number we had here, the better that percentage would match that percentage. Okay? So pretty cool. That's pretty cool. Now I'm going to give us one more that we're going to try together, and then you're going to try some on your own. All right? Let me grab my eraser. One more. Okay? For you guys right here, we're going to do this one, just to see if you can do this one. Uranium-234, Oops, I already did that one. I'm sorry. Where did it go? There it is. Uranium 16, 15.994915. Oxygen 17, oxygen 18, 16.999132, 17.999160. The percents, 99.757%, 0.038%, and 0.205%. Now you may be thinking, okay, what are you doing here? This is the exact same problem that I started with. The first problem that we did, I had oxygen 16 and a percent, 17 and a percent, 18 and a percent. Now I give you the real weights. Remember, we're just going to ignore that. Try the math, and let's see how close you get to the 15.999 that's on the periodic table. It's now your turn to try. All right? After you've done this one and you've done the math, check it. And then you can start the activity in which you're going to be figuring the relative abundance of some different elements. This will be found on your next test. It's a very, very simple math skill. You're doing a great job. Keep it up. Hope you've been doing all the problems with me.